According to the Child Mind Institute, approximately 80% of children with dyslexia go undiagnosed into adulthood, unable to receive the assistance they need in order to succeed in school. If an estimated 1 on 10 people have dyslexia, we can do a bit of math and find out that means that 80% represents 664 million people worldwide who struggle with an invisible disability and are just told that they're not trying hard enough. To tackle this issue, our idea is to develop a software that can differentiate the brainwave patterns of those with developmental dyslexia and neurotypicals. This would make diagnosing much easier and accessible to the wider population.
Our project tests for the potential existence of dyslexia, paired with the software that we have developed using data we have collected. We conducted a study to observe the difference in brainwaves between dyslexics and neurotypicals, and found participants through contacting organizations such as Hong Kong and Pathways Foundation. For our procedure, we conducted 5 tests in total. The first one is pronouncing non-words as a test for phonological coding and working memory. The next 2 are correlated as rapid automatized naming tests for retrieval and orthographic processing, while isolated naming checks for lexical access and articulation. We also used fluency to assess their automatic word recognition, and also checked for phonological awareness using phonemic segmentation. These tests have been derived from multiple sources, such as the International Dyslexia Association and research papers that examine the relationships between said tests and dyslexia, using fMRI and brain scans.
Alright, so once we collected the EEG data from both dyslexic and neurotypical participants, we used it to train our program to recognize patterns linked to dyslexia. First, we processed the raw EEG signals using M&E Python. EEG's data is noisy, so we cleaned up by filtering out electrical interference and motion artifacts. Then we standardized the signals so every participant's data followed the same scale. This made comparison accurate and fair without any potential bias. Next, we applied deep diffusion for further denoising. This model removes hidden noise while preserving meaningful brain signal patterns. It helps us improve signal clarity without losing important neural features. After cleaning and refining the data, we use machine learning modeling for pattern recognition. The model learns the statistical differences between dyslexic and neurotypical brain activity. It identifies repeated signal patterns across time and frequency bands and assigns probability scores based on those patterns. Finally, we integrate this system into a website with a user-friendly interface. The backend runs the analysis automatically, and the front end presents results in a clear, simple format so users can understand their outcome without technical knowledge.
So, our product is not only usable by professionals, but also by minimally trained individuals thanks to its simplicity. To aid in diagnosing English dyslexia in teenagers, this will be supported by our website, which will provide the necessary tasks as well as instructions for using the equipment and running the test. To run the test, EEG electrodes are placed on the participant's head, and the participant is asked to complete a task, for example, reading a randomly generated paragraph. After this task is completed, their EEG results are recorded, and patterns consistent with dyslexia can be identified, and these can then be used for diagnosis.
We hope that this idea would have a large positive impact on the wider community, and we thank you for your time.